So we had this framework, this conceptual framework of RINOs for neural operators, and then I looked at different examples, DeepONet, FNO, whether they are RINOs or not, and CNO at the end, which is a RINO. So now what I'm going to do in most of this lecture is to talk a little bit about the empirical evaluation and some of the caveats, some of the shortcomings of these methods. Okay, so let me start with numerical experiments, because in machine learning, it's a very important part of the entire process that they should work, whatever work means. And it also shows you some of the limitations, some of the caveats that exist with these methods. So I start with the Navier-Stokes equation in 2D, means all the tests are in 2D, that's the setup that we are in. And I don't want to write down the Navier-Stokes equations, all of you know what they are. And as I said, the operator takes an initial velocity field. I'm not showing the y, I'm just showing the horizontal components, not the vertical components. There are only so many things I can show on a slide. And then the operator takes the velocities to velocities, but you can visualize the flow in vorticity space because this is a vortex layer, and then the vortices are shed. So the ground truth that we are going to compare against is this object here. So this is the velocity field. X velocity field that we are going to compare, and I have tested various architectures here. So DeepONet, FNO and CNO, these are the three that I spoke about, but as baselines I have also looked at architectures that are not necessarily in this framework. For instance, UNet. So what is a UNet? It's essentially what we saw with an FNO, but let me just go back. So UNet is not an FNO, CNO. UNet has this kind of architecture. It has some of these layers removed, and these modulations are not happening. So the nonlinearities and the convolutions are not modulated. So it is not a RINO. It's just, let's say, the base on which a RINO is being built. And then the last one was just a fully connected neural network, feed-forward neural network. This is an MLP. So where each point is treated independently. And then this is what I covered, for instance, in the parametric PD setting. So now let me show you some test results. So this is how the results look like. These are the numbers. As you can see that they are what they are. So FNO is approximately 4% of test error. CNO is so first of all, how is this data distribution generated? Because there are many questions about that. So the data distribution is generated by taking some base flow, which is a vortex. This is a very well known benchmark for CFD, first invented by Colella and Bell and so on. So what you do is that you perturb the vortex sheet with some sinusoidal frequencies. We do not have access to Q&A. Okay. Sorry. And then you have some random shifts here. So there is a probability distribution from which this is done. And these are some of the results. So clearly CNO, FNO, and UNet do very well. DeepONet does very poorly on this. I told you about some expressivity properties with DeepONet. So as you can see, it is not able to approximate the details of the flow at all. It is approximating what would be the mean flow. If I would have taken 100 samples, then this would be how the mean would look like. So it's able to approximate that, but it is not able to get the variance or the details in some sense. These pictures are not very useful, but they say something. For instance, if you compare the CNO with the CNN or the UNet, you can see that there are these kind of patches on the UNet. On the FNO also, you see that there are these kind of little artifacts which are sort of coming out. And you will see in a minute what these artifacts are. Because these are important, right? So this has to do with this aliasing and with the entire theory that I presented. So now these are, remember that for a neural operator, it's not enough if I show you results on a single resolution. We should be able to change resolutions, right? So this is precisely what we do. We trained on 64 squared. Now we're evaluating on 32 squared, 96 squared, 128 squared, and so on. And you can see that with both the UNet compared to the CNN, it's a bit better, but with the UNet you have, it's not a RINO, so the errors go up as expected, almost 3-4 times, right? They go to 14% from about 4%, and also FNO. You have already seen this result before. FNO has the same kind of U-shaped behavior, so it's not a RINO. CNO in this case is a RINO, so you have a flat line here. Okay, so this is exactly based on the construction that we have presented. Now, a lot of information about this kind of performance can be gleaned from the spectrograms. If you look at the spectra, so these are the this is just the spectrum of the solution, the ground truth. As you can see here, it's a fairly rich spectrum because we are taking 32 frequencies in both directions. So it's a fairly rich spectrum which is populated here. It's taken logs, otherwise you don't see anything. The dominant frequencies will crowd out everything else. And if you look at the approximation of the CNO, it's not a perfect approximation. That's why you have 3% error, right? It approximates sort of the central frequencies quite well. It has some artificial features here, and then it doesn't do so well here. It has a bigger cutoff. So this is where the approximation is. But if you look at both FNO and UNet, what they do is that they create some artificial high frequencies. This is very, very visible here. You have some high frequencies where none exist. And also for UNet, as you can see, that these are these high frequencies. These are precisely, we believe, signals of aliasing, because aliasing implies that high frequencies come in and where they shouldn't be present. And since we are not filtering them out, this is what you would expect. So these kind of pictures are sort of consistent with the results that we see here. So from the spectral behavior, you can get some additional information. The next point, which is very important, is again for some reason. And this is a very, very important point that I have to repeat time and again, that usually people show you pictures. I also showed the same, that I showed you some numbers like this and then said, okay, one model is better than the other. But this is, there are lots of caveats to this, and one should remember and understand these caveats. So this is based on a certain amount of data, okay? And remember that after all, when you change the amount of data, the error is going to change. We expect this sort of a square root type behavior or fourth root type behavior, and so the error is going to change. So here is just a comparison between FNO and CNO. Other models are also there in the paper, where you go all the way from 32 samples, just in distribution, to all the way up to 1024 samples. And you would expect that as the number of samples increase, your models should scale. Means, this is the expectation, and it does scale. Suppose I would have stopped at 32 samples, FNO would have beaten CNO, because one is at 9% and the other is at 11%. But the rate of decrease is much faster here, as you can see. And these kind of plots are very, very essential, because they tell you that asymptotically there's still no saturation. So yes, please go ahead. Now we have to go through the enchilada. I can take it if you give me. You have to exercise. Huh? Yeah. Yeah.
Actually, I was wondering, what are you computing actually? What is the input, the output of what you're showing?
I said that, right? So I will show it again. So the input are the velocities which are given by this here, and the output is this velocity.
But that is, you have a fixed time, or you can change the time?
Yeah, no, this is a fixed time.
And how far you can go in the horizon for the time?
Well, it depends. Here we only went up to t equal to 1, but it depends. Means if you only have a fixed operator, of course, as you go further, the error is going to be naturally larger, right? Otherwise, you can do autoregressive. I will have some comments about that later.
Okay.
But here I am just comparing things in a fixed
time, one time.
At the time one. Okay. As you can see, this is not that bad, because if you wait for too much of time, these vortices, the vertical information is lost, the vortices get dissipated, and so the interesting here is the transient. It's not the long time behavior for this particular problem. Okay. So in this particular problem, what you are interested is when the vortices are shed and when they're slowly starting to merge. So if I would have waited too long, they might coagulate, and maybe it's not so interesting from an application perspective. Okay, but it's a good question. And this is sort of a fixed time. So you start from a fixed. So the operator starts at t equal to 0 and then goes to a fixed time. I'll say something about what happens when time varies later. Okay, so anyway, that was a good question. And then this is a very, very important point. So usually how the operator scales, or how the neural operator scales with data, is a very important point, right? So now this is quite convincing that neither of them are saturated. They will probably go down further, and there is an asymptotic difference between the two of them. Then the next point, which is also very, very important, was raised during the lunch break. And this is the question again about generalization. Means everything is generalization. So somehow in machine learning, very roughly speaking, Generalization is when you try to apply your model to something it has not seen before, and how well does it do. This is roughly generalization. So you could argue that already I covered a bit of generalization because, for instance, this one here, because it had never seen grids of 228 squared, or it had never seen grids of 96 squared, and yet I was able to evaluate on those grids, and you saw the performance. So that's one aspect of it. There may be various different aspects of it. Here the aspect is slightly different, that I changed my distribution itself. So the way it is changed now, the details are not important here, is in distribution, remember that I had this shear layer, and then I had this sinusoidal frequencies on top, and then I looked at the output at a fixed time. Out of distribution, I perturb this measure. Of course, I don't dramatically change it. I don't take a shear flow and then go to a channel flow. And then this is asking for too much. But what I do is that I shift it and I increase I make it thinner. I make the sheet thinner so that you have much more vortical generation. The vorticity becomes much richer, and you can already see it a bit here that there are more structures that are being generated. And then I can apply my model, and the model can always be applied. It has been trained to take, if I would have done it in a parameter dependent manner, this wouldn't work, because in a parameter dependent manner I have taken more parameters here, whereas in this setting I can always take any input and feed it to the model. And this you see FNO, CNO and UNet, and this is the sort of picture here, and you see this is how the generalization performance is. So they don't they generalize, 3% does not remain 3%, or 4% does not remain 4%. For instance, instead of 4% you go to, and sometimes this is also called zero shot learning, because from here I am not giving it any additional information. No samples are used on this distribution. We are directly evaluating the role of this. If you want to do few shot learning, I could have retrained my model with a few samples of this, but I don't do it here. And then you can see the generalization performance is what it is. CNO, of course, generalizes better among the others, but this is what it is. And the point is, why do I emphasize this? Because I started at some point about numerical methods, and then you should be able to compare with respect to numerical methods, right? So here is one sort of a comparison. You can argue whether it's a fair one or not, because for this particular problem, it's also in 3D we have a very, very accurate, probably the fastest spectral code in the world, sort of GPU based and multi-GPU based, and it goes as fast as it gets. So on this, for this 2D problem, for a 100 square grid, the runtime was 1/10 of a second. For the traditional numerical solver, the error was approximately 2% or 3%, whatever. Here it's a little bit more, but our inference time is 3 orders of magnitude less, right? So in that sense, you can say that it is competitive because it has not seen this data distribution before. It has only seen the distribution there, and in a zero shot manner we are trying to infer it here. Of course, yes? What's the accuracy of the spectral method? The spectral method will get you 2 to 3%. So it's more accurate than this is. No, now I can say it. I said it. Bruno, it's okay. Oh, you keep the mic there. Okay, but that's good. I like it like that, right? So this is one way you can think of generalization in this particular context. So this is one thing that you should remember, that I think Jin Shao asked me this question about distributions, right? So of course this is not dramatic, but it is a different distribution, and it has never seen the distribution. So you can ask it to see how it evaluates and how the performance is.
Since you mentioned
just a question.
What's the discrepancy between this out of distribution and in distribution? What's the difference between the two?
In what sense you want to?
Test error. What do you measure in the test error?
No, the test error is simply that.
In the error 2 norm, or what is it?
This is in L1, I think.
You take the error 1 between those two initial gas.
No. You take the L1 between these two.
I understand.
Yeah.
Because your initial gas is out of distribution,
Yes.
right? So, but you also mentioned that it's not a dramatic out.
No, so you want to know how much out it is.
Yeah, what's the percentage?
Yes. So it is very difficult to compare now, because this is these are measures, right? So they are not really functions anymore. These are measures. So I would say that on the Wasserstein metric, It could easily be anywhere between 10 and 20%. So they're not, they are far from, I know your question. Your question is it just a question of stability? No, no, no. These are, if you just look at these two, they're not very similar to each other. Means the outputs, see? So this is not purely a function of model stability. So they do learn something. But it's difficult to quantify because now it's a distribution, right? So there are two measures. You can, of course, quantify them in the Wasserstein metric, but then what is the meaning of a percentage anymore, right? So if you take an average sample from the two, so I see your point, but I think we are safe. You can't just apply this model that way. So here, this is sort of an important point, perspective that one should have. And then, what did you say? No, it's okay.
You look close.
But they are not close. These two they look close to you?
The output and the input.
Of course, the input is, this is the whole point of a turbulent flow, that the inputs can be close, but the outputs aren't, right? This is,
What's the Reynolds number?
well, don't ask, because this is like 10 million. This is an incompressible flow. This is an inviscid flow, so it's like 10 million. This is incompressible Euler. So that's correct, 10 million or something. We wrote the number, but it's a very high number. And this is also very important, that one shouldn't just look at these numbers in a point-wise sense. One should also look at the error distribution, right? So here is the error distribution, and this is even more convincing in some sense. Let us look at the sort of, let's say, the out of distribution errors, right? You can see that the distribution is peaking around 5%, quite a lot are around 5%. The other ones are more peaking like 10, 12%. So in terms of out of distribution, it does much better than this does in distribution. Of course, I should say that everything is done fairly, but training of neural networks, there is always training errors, right? So we keep that in mind. So these are some of the sort of evaluations that one should do. Very important to check, for instance, scaling with respect to data. Also very important to check things like out of distribution performance, zero shot learning, few shot learning, and so on. And also to check the whole error distributions rather than sort of fixed points. Let me give you another point here, because means how do you choose? Means there are lots and lots of papers on operator learning and in general on machine learning for PDEs, and they are sometimes not written by people who do numerical analysis for PDEs. So they take problems which are sometimes not very representative of what you want to do. For instance, if you remember, this is the problem that we started out with. This is the vorticity to vorticity mapping, and there are hundreds of papers which use this as a benchmark. And of course, we can also try our method on this, and you see that these are like 1% does not really matter. But the point is that now the spectral, this is not a rich enough problem. Why is it not a rich enough problem? Because if you look at its spectral structure and compare it with the spectral structure of the other problem that I showed you, the one which is more, let's say, turbulent in some sense, even though it's only 2D, then you can see that the spectral structure is here is not very rich, only few dominant frequencies, and many others are going to die out. So in fact, if you do the numerical method here, with 20 by 20, you get the same sort of errors. So this can be done in like less than 1/1000th of a second. And remember, whether it is CNO or FNO, we need only 1/10,000th of a second. So already the numerical method in this case is so good that you don't need a surrogate for this. So in other words, some problems can be too easy, whereas the problem that I mentioned, that requires many more sort of modes in order to be represented. So somehow you need a rich enough set of problems, and this should always be remembered while using these methods, because if you take a very simple problem, of course a numerical method will do very well, and why do I need a machine learning method to solve it? So to test it, I need a little bit more structure. Of course 3D would be perfect, but let's start with 2D, and this is a point that I wanted to make. And then there are lots of examples here. Maybe I give one more in some detail. So this is just a Poisson equation. It's as simple as it gets. But it turns out that it has a little bit more structure. So now, of course, I will not find the chalk. It's just a Poisson equation on a square. And it's not even, so it's minus Laplacian of u equal to f. and u on the boundary is 0, and then the operator G is a mapping from F to U. So it's as simple as that. The histograms are done. Someone is asking a question. Can I check it, or if you can read it?
I will read the question.
Yeah.
The question about the fact that the histograms are done on different trainings.
No, but they are done on different testings.
Okay.
They are not done on different trainings. One is done in distribution, and another is done out of distribution. So there is this is the answer. Not to you, but to the person who's asking the question. Okay, so this is just a Poisson equation. We can. There doesn't seem to be. Yeah. Bilal is the person who asked. Bilal Ben Said. Okay, so now you can see that my F now here. This is this object here, so I have put lots of frequencies to just make it a slightly difficult problem. Otherwise, I can solve it with a finite element method very easily. And then my output, of course, is more because these frequencies are damped. This is a inverse Laplacian. So this is the input-output map, and there are different predictions, and yeah, whatever it is. Means you can see again DPONet does very poorly. It doesn't do a good job because even though it's a linear operator, it doesn't learn the basis well. So it doesn't do a good job. Both CNO and UNet do relatively well. FNO doesn't do well. I mean, this is one of the problems where FNO doesn't do well, either in distribution or out of distribution. Out of distribution, you simply increase the frequencies. I think this was 16 frequencies, and this is 24 frequencies, or 24 and 32. I don't know the exact number, but you have many more frequencies. And then you look with CNO, for instance, the performance is almost invariant. With FNO, there is a big difference in performance. But this is just some examples. And I have many examples that I don't know how much of detail. Again, the same questions come up. Resolution dependence. So resolution dependence, again, as expected, what you saw. So here there is some numerical error. So it sort of goes up, and also it's hitting towards the Nyquist barrier. So you see that there is some increase, but it's mostly more or less constant. And you see the same with the spectral behavior, that high frequencies aliasing is polluting the solutions, and as a consequence you have a drop of performance. So whatever I was talking about is not just some theoretical artifact, it has some practical significance. Wave equation, I think I'll skip it. Alan-Kahn, so the one-dimensional version of Alan-Kahn, this was the same story with the wave equation. One-dimensional version, Alan-Kahn is this equation that you are going to see later today in our, so you don't have to put on the light, it's sort of, I think there's an epsilon here, u1 minus u, roughly speaking. So this is the Alan-Kahn equation. It's supposed to model phase transitions, and in the exercises today, we are going to do Alan-Kahn as the one-dimensional version of the Alan-Kahn is going to be the task, right? So this will be our solution operator. It takes solution at a given time, and it maps to solutions at a later time. And here, for instance, you could see that FNO actually does better than CNO. So there is no universal, there is no universal approach. One method can do better, one method can do worse, means this is how it is. DPONet does very poorly, again, because this is, as you can see, there are rather sharp gradients in the solution, and as a consequence, it doesn't get them well. One more example that I would, two more examples, and there is a story here, there is a moral here. So this is just advection, okay? But it's two-dimensional advection, so I have a fixed velocity field, and I'm simply advecting this patch up. But now during training, what I'm going to do is that I'm only going to train the patch with different heights and different locations in this region here, in the bottom quadrant. And then I test it also in distribution. For out-of-distribution testing, what I do is that I simply translate it, okay? It has not seen translations before. But if the model has translation invariance, then it should realize that it's just translations. So I should be able to realize that. Now remember that CNO and UNet is by construction, these are convolutions are translation invariant or translation equivariant. So they are good with respect to shifts, and you see that means there is virtually no change in the in and out distribution performance. But FNO, for instance, it does a very good job as it is supposed to do in terms of in distribution. But in out of distribution, it does very, very poorly. And look at DeepONet, for instance, means it has pathetic results when it goes to out of distribution. Why? Because there was no notion of symmetry for these models, and they could not deal with something that is a symmetric perturbation or symmetric deformation. You can see, for instance, the DeepONet, it still keeps a huge patch here, FNO2, and DeepONet, of course, has a very, very poor performance. So sometimes these factors, invariances, symmetries, these also play an important role. As a final example, this is the example that I started with, which is compressible Euler equations, the equations that I know the best personally. So always has to be something. So this is now the operator is shape. Okay, this is shape is as a, or you can put it as an initial condition also in terms of the level set function, and the output is the steady flow. So we are looking at t equal to infinity, the steady flow, because that's what we are interested in. And this is the density distribution or the pressure distribution, for instance. In distribution was with these 20 shape functions. Out of distribution was with 30 shape functions. So the airfoils look a bit different, but now you can see, for instance, how the performance was. There's not a huge difference. They did rather well. And here the point is that when I do this testing with a numerical method, it takes me about 2 minutes to get similar sort of accuracies, 2 minutes of simulation, whereas these guys are still like 10 to the power minus 4 seconds. So already here you see that there is some performance increase, and you can already see in the out of distribution, for instance, that there are these artifacts which are visible, which are not there with the in distribution, right? In distribution they were quite good. So there are these kind of examples. I can go on, but I have to stop with some examples at some point. And maybe I said interim summary, but it's become a summary because I don't have that much of time. Where the model here, someone is asking a question again.
Yeah. The question is the following: Do you think we can reach greater precision with these techniques, like the ones we have with traditional numerical methods?
No. This is a question that is often asked, so I think greater precision than what means like 10 to the power. By the way, for a numerical method also, to reach very low precision here for these hyperbolic problems is not super easy, as we know, means very refined mesh is, I know, I'm just answering that person. So I think for an engineering perspective, it's enough to do with, I think these are very accurate results. For me, means 0.47 or 0.35% is very, very accurate. I don't need any further accuracy in this particular case. And there's another one who asked something about optimization. No?
Okay, thank you.
No? Isn't there one more? It's the same. I see. Okay. So let me just summarize some findings, and then I talk about some perspectives. So essentially, okay, for essential, but operator learning is one option for machine learning in PDEs. But at least for operator learning, the notion of continuous discrete equivalence is very, very important. And this was sort of my main point, because without that, you have aliasing errors, and you saw some theoretical as well as practical manifestations of how aliasing errors can affect your solution. And what the primary theoretical tool where we described it is representation equivalent neural operators, or ReNOs, which enforce continuous discrete equivalence. There were some conditions for DeepONet and FNO. DeepONet and FNO are widely used algorithms nowadays, means at least in academia. And there were some conditions on them to be ReNOs, and we also described CNO, which is a convolutional based ReNO, and I described some numerical experiments. But perhaps it is sort of important also to talk about some for CNOs, but in general for these kind of models, what kind of caveats and what kind of questions are remaining. One of the most important thing is that, okay, you always should test on more problems, right? We had like 7, 8 test problems, but maybe you need 30. But more importantly, you need to go to 3D, because a lot of the tests are done in 1D. 1D is useless because the numerical methods are very good in 1D. You don't need 1D. So 2D is a bare minimum, and there you really need to benchmark it against numerical methods to see some advantage. But if this works in 3D, and this is a big if, there are some tests done with DeepONet and FNO, but if it works in 3D, then there is a big gain, because there is no 3D solver that will give you results in 100 seconds. especially a 3D flow past an aircraft solver does not take 100 seconds. So there will be big gains. I did not describe so much about non-Cartesian geometries. Non-Cartesian geometries, of course, are much more important. DeepONet, by definition, can work with non-Cartesian geometries. There is no issue. With both FNO and CNO, you need to transfer the problem or transform it into a Cartesian geometry. But this can be done either by learned isomorphisms or diffeomorphisms, or by adding some other features. So this is a topic that has been covered by, for instance, for FNO by many people. Another point, I think you described it, was a question of time marching. So there are two ways in which you can do time marching. One is by simply taking a long enough time horizon. The second is by doing what is called autoregressive time marching, which is that to go from 0 to 5, you learn the operator from 0 to 1, or you learn the sort of increment of the operator, then you go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. There are many ideas out there. Usually the problem is that there is some accumulation of error as time progresses. There are some strategies, Emmanuel, for instance, is an expert on this. There are some strategies on how to control this error. So this is still not a closed story. And then there is a question of data, right? Because there is always issue of how will we get data. As I showed you, more data, models perform better. But more data also requires numerical solvers or experimental data, and that's expensive, right? So one way is to use what are called PIN, or physics-informed losses. So you could also combine FNO, DeepONet, CNO with physics-informed losses. So the model itself is a neural operator, but on top of it, you for instance, use this in your loss function. So you take this operator, take its residual, and then try to minimize the residual. People have done some attempts on it. This is still very much an emerging research topic. This is what I said, PIN type PD residual based loss functions, and this has been done, as I said, means in some contexts, but we have not done it for CNO, but this is an important topic. It's unclear how good it is at generalization. Maybe it's very specific to the problem that you're solving, and then we change the problem slightly. It doesn't really help, but this is a question. And of course, there are questions like out of distribution generalization. So far, what I showed you was deformations. I changed the inputs and outputs, or symmetries. I used a different symmetry group to perturb the inputs and outputs. But beyond that, when you have very general measures, this is certainly an open question, if not at least to say the least, right? But there are some, let me see, yeah. So there are some other approaches to operator learning, means I just showed you, or generally applying ML to PDEs. For instance, a lot of people these days use graph neural networks, GNNs. We have also used it in my lab. So and in industry, this is tech industry, this is very popular. You have mesh graph nets from DeepMind, some algorithms from Microsoft. Then you have variety of architectures which are based on transformers, some from us also. And then there are some which are based on encoders, autoencoders, and so on. So there are many, many different architectures out there. What I can say is that, who knows, maybe some of these architectures are quite good, but there is not yet a thorough investigation of continuous discrete equivalence. Means how well do this retain sort of continuous features? These are all discrete representations, but how well they represent the continuous features, this is still very much up in the air. Some of them don't, we know that for a fact, but some others might very well be. How well they are in out of distribution generalization, this is still sort of very much up in the air. There are many different questions that come up, and if anyone is interested, you can approach me offline, and I can tell you what I know about some of these architectures and what I have done. And then, of course, there are downstream tasks. Once you have the neural operator ready, you're going to use it in some context, right? And the contexts that I had already described, they are uncertainty quantification, PDE constrained optimization. These are examples. Optimal control, Bayesian inversion, because this is much cheaper than the solution of the PDE itself, the numerical solution of the PDE itself. And the last point is about PDE inverse problems. And I think I have approximately 20 minutes, and then I'll use those 20 minutes just to show you something about PDE inverse problems. But before that, are there any questions on this? Yes, Frederic.
Well, my question is about the result for the Poisson equation
Yeah.
and advection equation for the FNO
Yeah.
neural network. So in the Fourier basis, solving the problem is simply multiplying by the inverse of a polynomial. So it should be easy.
It should
the
be easy.
results are poor, so why?
Yeah, I think I already gave you a hint, but it should be easy. But remember that FNO is not just Fourier inversion, right? It has some nonlinearities on top, it has some weights and so on and so forth. Our observation was that this was to do with the fact that the scales become very different, right? So maybe Roberto, you know this better than I do because you actually trained it. And maybe, no?
Yeah, I think it was.
Maybe he actually trained it, so he knows the exact answer. So I know the answer from him, so he can as well directly give it.
I think it has. I mean, in practice, you might solve it even with one layer. But the issue is that when you compute the Fourier transform of the when you move to the Fourier space, you get a scaling factor in front of f, which is 1 over the frequencies, and then it can become or the opposite, it can become very large, and so it can be difficult to learn to tune.
So it is pure. Huh?
Sorry.
Yes.
I mean, maybe you can start with the different initialization of the parameters.
Yes. So if you, so the point is that you start with a certain initialization of the parameters that is based on the normal distribution, and for going from there to this global minimum, because there is a global minimum, is not so easy. So you could start with a different, but then it is like finding the solution for a problem that you have already solved, right? So we don't want to do that. So if you apply it directly, it finds it very difficult to go from a, so it's in the training process. The training errors here are relatively large. If this is the case, right? So they are relatively large training errors, and this is reflecting the fact that it's not so easy to go to the global minimum, even if we know that there is a very simple global minimum. So this is always an issue with neural networks, how well you train. So it's sort of, yeah. Okay, any further questions? Yeah, there is a question at the back. Now it's sort of, you have to really shout. No, I'm kidding. Shouting is not allowed.
Yeah, thank you for the talk so far. I was wondering if there has been some research into whether what kind of features the layers learn or something, because, like, for example, image analysis or image recognition, there's like research in what structures the networks learn to detect in the image. So is it, can you like make some, say that it learns the underlying physics or something?
I got your question. Interpretability is essentially what you are asking for, means what exactly do these layers learn. We haven't done this systematically, but here is my hunch. At least with convolutions, we do exactly the same as convolutions always do, which is that the first layers learn the sort of low frequency features, and then the higher layers learn the high frequency features, and then they combine them together. So this is my belief, right? I'm pretty sure that that is what happens. FNO, we don't have that many layers usually. You know, how many? 3 to 4 layers is the ballpark. So I think I don't think anyone has done this. We have never looked at the outputs of the layers, because anyway they are sort of complicated because they are in some latent space which is sort of high dimensional. But it's a good question. Maybe this is sort of, there's a lot of literature which is emerging on different notions of interpretability, mechanistic interpretability and so on, coming from large language models. It could be interesting to try some of those ideas here. We are doing baby steps. You know, this is what, for instance, image was in 2016 maybe, or 2015, or text was in 2018. Means we are far away from those kind of questions. But it's a very, very good point, and it should be done. Yeah. Yeah.
I just wanted some clarification on the errors.
Yeah.
First, I guess you said before that for the velocity, you measure errors in the velocity in the L1 norm.
Yes.
Did you look at the vorticity errors?
At some point we have looked at it, but it's sort of, you could look at it. Of course, the vorticity errors would be large because it has never seen any vorticity whatsoever. But I don't know if you did it systematically, but one thing that you could look at is how the vorticity errors behave with respect to data. So this plot, I'll show you the exact plot. For instance, I would be very satisfied if this is in velocities, okay? And I would be very satisfied if similar, even though it has not been trained for vorticity, if the vorticity goes down also probably from a very high number because it has never seen the vorticity. So how is it going to learn the vorticity? If this also goes down, means I believe that it does because it's approximating something reasonable. So, but of course, controlling the velocity is not giving a control on the vorticity, right? I mean, this is this has not been trained there, right?
Yeah. The second quick question I have is actually, what is the error from the numerical method?
Yes, he also asked this question. It depends on what resolution. So, for instance, if you are at 100 squared, so the ground truth is calculated by doing a spectral method at 1000 squared, right? This is the most accurate, or 512 squared or 1000 squared. So, the error of the numerical, at 100 squared, you get 1 to 2% error. So, this is sort of the ballpark error.
1 to 2%?
Yeah.
Sounds quite large.
Yeah, but this is how it is. This is not an easy problem because this is sort of, we even have a picture of it somewhere, no? Yeah, so I don't know how well you see it, but you see for 100 it is about, it's 2% roughly. So, but this is the numerical method is what it is, means this is not an easy flow, means it's, where is it now? So, it's really about 2% for 100 squared, and that's what you are comparing with. Oh, now I have lost it. It's irritating that it's, so this is, it's about 100 squared is about 2%.
Okay, and the last question I have is, could it be reasonable actually if you give an error level as a benchmark, okay, you want to reach a certain percentage, like 2%, okay, then to reach that you will need a certain number of samples, actually you show the curve, but this is a cost also because you will need to run the model for many, many samples. So somehow at the end of the day, isn't it the performance measured by actually including also this offline cost?
It is, it should be mentioned. That's why I intentionally did not, it's a good question. That's why on purpose I did not show you the computational complexity on the in distribution. But remember, for the out of distribution, it's only fair to say that this has never seen this input output map. It has not, because this was not in the training samples. It is something that we are using it to extrapolate rather than to interpolate, right? So it is only here that I am making this comparison, and I did the same for the compressible Euler. Of course, that is, for instance, in the parametric PDEs, I don't want to go so far back, but if you remember, I had these pictures of uncertainty quantification where there was a factor of 10. Factor of 10 sounds like, okay, it's not a big deal, right? Because there you have only, there is already 3 orders of magnitude here. So where is the factor of 10? There the training error was included, because I could have used the training samples to do my uncertainty quantification. So it depends on what is a fair metric. Sometimes it is fair to compare, sometimes it is, the offline is not fair to compare, right? So this is, so there is much more of a, let's say, one has to be careful. One should not always say, oh, machine learning methods are the best. There has to be a case that has to be made, and in particular it cannot be made in 1D, because your numerical methods will always outperform machine learning methods in 1D, unless until you are looking at very long time integration or something like that. So 2D is where you can start making the case, and surely if these things work in 3D, you make the case, right? Because in 3D, nothing, to get 1-2%, you are not going to spend 100 seconds, you are going to spend 100 minutes. So then it starts getting competitive. Okay, so there is a nuance here. So let me very quickly cover a little bit of PDE inverse problems, but I don't know how much of time I would have. But it's sort of an interesting, I prepared for it, so I show it. Okay, so I will be quick now. So I will not be slow, I have to be quick, and please read the paper or ask me or Roberto if there are questions. So let's say that there are a bunch of inverse problems. Now we are in France, so many people here know about inverse problems. So for instance, a well-known problem which comes from what is called electron impedance tomography, EIT is the so-called Calderon's problem. What is the inverse problem here? So you have a PDE. So this is the variable coefficient Poisson equation with some boundary conditions. So this is essentially the coefficient is your conductivity, which is supposed to contrast with your internal organs in the body, and then you put in voltages. G is the voltage, which is put on the boundary, and then you can measure the current at different locations in the boundary. So this is sort of, and the goal is to infer the conductivity from these measurements, right? So this is one example, the so-called Calderon problem. And then I have to stand here so that I can go more quickly. So this is optical imaging, where we use the radiative transfer equations, some PDEs, and then the idea is that you put information on a part of the boundary, so-called incoming or inlet boundary, and you make measurements on the outlet boundary. And the objective is to measure what is called the radiation intensity, the absorption and scattering coefficients from these measurements. And the last example, which is a very popular one, is seismic imaging, where you send in waves and then you measure the reflections at different locations, right? So in this case, for instance, you're solving the acoustic wave equation, you can solve the elastic wave equation. The A is what is unknown. You send in some sources, some, let's say, waves into the medium, and then you measure at different recording stations. Of course, the point is you have different source at different points of the source and different measuring stations. So all these problems, they can be put in the following abstract framework, that you have a PDE, which is given, and then you have some boundary conditions. I focus on the boundary conditions here. And the observable, what you measure is always on the boundary. And actually, it is not just a function, it is what is called an observation operator, because you change the location of the source and you measure at different locations. So for a different value of the source, you get different answers. It's the same, for instance, here, here, that you change the location of the voltage and then you measure current over the entire boundary. So in other words, your objective is the observation. The observable is this boundary observation operator, which takes a function on the boundary and returns another function on the boundary. For instance, voltage on the boundary to current on the boundary. And then in this case, the forward map, it takes the coefficient and it turns out this observation operator. So the inverse map, which is what we are interested in, is given this observation operator, I want to infer my coefficients. Or in other words, given lots of recordings of the waves, of the wave intensity, I want to observe the seismic distribution and so on. And one of the beauties of mathematics in the last century is that we could prove rigorously, not me, but giants in the field such as Calderon and so on, they have proved that such an inverse map, which maps between an operator and a function, this actually exists, is unique, and is even stable. It's stable. Of course, sometimes the stability is just in terms of a logarithm, but there is some stability result. In other words, the inverse map is a mapping between operators and functions. So earlier we had operators, which is a mapping between functions and functions, but the well-posedness of this problem is in a setup where it is between operators and functions. So, and there are different examples. For instance, this is the observation operator is the Dirichlet to Neumann map. Some of you might have seen it. Here it is called the source to receiver map, and so on and so forth. So these are, in some sense, at least some of them are provably well-posed problems. So usually what people do is that you do some sort of PDE constraint optimization. It's an iterative method. You start with the guess of the coefficient, you solve the PDE, you make an adjustment, solve the PDE again, make an adjustment, solve the PDE again, and make an adjustment. It's expensive, and because of this weak stability, you need some good starting points, good regularizations, and so on. So in no means is this a solved problem. Our approach and approach of some other people is that why don't we learn this entire inverse map from the data itself. So you generate a lot of data, and in this case we have quite a bit of data. You generate a lot of data, and then you learn this mapping, which takes operators to functions. So it's a generalization of what we have, which was functions to functions, and we call this mappings as neural inverse operators, because now this is really an inverse operator. So this was proposed in this very recent paper, and I very quickly give you some results and some architecture. This is a downstream task, right? So again, the invariance here, or the the continuous discrete equivalence is that this observation operator that we were talking about, this A lambda, now this, of course, it's a continuous object, right? It's a map between functions and functions. So now you have to only sample it, and you sample it from a distribution. You have X number of samples. How well does it do with respect to this number of samples? Ideally, we should be invariant with respect to the number of samples. So that's the discretization invariance that we are targeting. And there is an architecture. The details of the architecture are not important here because I simply don't have the time. But it's essentially combining some of the things that we have learned, which is that it takes a DPONet and an FNO, and it sort of concatenates or composes them. And the reason why it does so is because the inputs are given on the boundary. So the DPONet takes the inputs on the boundary, converts them to the interior, and then you process them through an FNO. So this is roughly the objective. And there are many other tricks, particularly some randomized batching, how we could make it discretization invariant. But this is some sort of a detail. The important perspective, point from my perspective, is that you combine DPONet and FNO. You could also take CNO, for instance, but FNO is just what we chose. And it does work quite well. I'll show you how. So this is an example of what is called a heart and lungs phantom. It's a medical image. You have these kind of inputs. And from these kind of inputs, you have to infer this object, and okay, there are some comparisons here. And you can see that the main point is that it's really invariant with respect to discretizations. In other words, I might have trained my architecture on 32 samples of the Dirichlet to Neumann map, but I test it on 30 samples, 25 samples, 20 samples, 5 samples, and so on. And we are almost invariant with respect to this. Whereas the competing architectures, which have not been designed, just like FNO wasn't designed, you can see that the error really jumps up. So here also this continuous discrete invariance is very, very important. And when you take traditional methods, these are not traditional numerical methods, but traditional methods for inverse problems, for instance, the so-called D-bar method, you can see that we are very much more accurate and much faster. So now in inverse problems, this really pays off. Because you can see that the D-bar method, it gave you 9% error and it took 2 hours. This gave you 0.18% error and it takes 0.1 seconds. Of course, this has been trained on some data. So whether the comparison is fair or not is a good question. Then let me show you, maybe this one, I like this example. So this is Helmholtz. Again, many people here have worked on the Helmholtz equation. So what you have is that you have these obstacles or scatterers inside a domain. You send in waves which are time harmonic, and then you have these kind of measurements, and from this you want to infer these guys here. And okay, there is some out of distribution. We define something out of distribution, and this is not important. The important point is, for instance, here. So we have our architecture and a competing one. And you can see, for instance, you completely miss the, you miss this scatterer completely in the other architecture, whereas here you resolve it quite well. And again, this discretization invariance, this is the key. So it's similar to changing the meshes, but now you change the number of samples for the map, Dirichlet to Neumann map, and you see a flat line here, whereas the competitors are completely off in some sense. And here's another example. This is a fair comparison because, again, it's out of distribution testing. So on the extreme right is sort of PD constraint optimization, more or less a state-of-the-art method. It takes 9 hours to solve this problem, and it gives you 11%. Whereas this method, which has not been trained on this particular distribution, it has been trained on a distribution which is near it, but not this particular distribution, it gives you 2% errors at 1/10 of a second. So you get a lot more accuracy and a lot less time. Of course, there is some training time that we shouldn't forget, but even that is not 9 hours in this particular case. So we are, even with the training time, you are beating the numerical method. So this is an example. Maybe you have the same kind of picture for optical imaging, and how it changes with respect to data is an important point. And I'll just finish with the example on seismic imaging. So these are sort of the measurements. So these are the location of the sources, and this is how these sort of impulses, these responses come in. And from this, you have to infer this coefficient here. And again, with respect to another architecture from people at Los Alamos, it has the same performance. But remember that success is never a point, it's always a line. So in this case, when you change the number of samples, this remains exactly the same, whereas the competing methods, the errors go up by a factor of 10. So this notion of continuous discrete equivalence is very, very important. And here again, when you compare with a numerical method, PDE constraint optimization, you can see that the errors are reduced significantly, and the inference time is, of course, what it is. It's much, much faster. So for inverse problems, there is no doubt that there is a payoff. There's a big payoff when you use these particular methods. So okay, I am more or less done exactly on time. So I showed you different operator learning architectures. Both, okay, I didn't really have any time to explain to you inverse maps, but at least you have seen it. And one of the main points I wanted to make is that whenever we are learning operators or objects like that, it's very, very important to ensure that there is this continuous discrete equivalence. Failing it, you don't have stability or invariances or generalization abilities, and then you might pay a price. Okay, so with this I stop, and after at 3:30 I think we have the practicals where you'll implement DeepONet and FNO for the Allen-Kahn equation in 1D. So this is something that can be done. Okay.
Okay, so thank you very much. So now we can thank you for